To start out this video, I want to remind you of something we found in the last video. A change in kinetic energy. 1/2 m v final squared minus v initial squared. That is my delta k. Of course, you can distribute the 1/2 m if you so desire. But this is a change in potential energy. Okay. Now, we also have talked about, not in the last video, but in previous videos, the idea that work, if I write down the equation for work, integral from point A to B of some force F dotted into some differential displacement dr. I said that you can use this expression to investigate work done by a specific force, maybe work done by gravity or friction, or you can use this to investigate the net work, that is the work done by the net force. It works both ways, and in most cases you get different results depending on what you're doing. So first thing I'd say is be careful how you're using this. If you're using it to investigate one force, make sure there's only one force here. If you're using it to investigate a net force, what that means is you have to put a net force here. So let me write how we would write that in that case. The net work is equal to integral from point A to B of the net force, right? We've seen that before. Net force dot dr. Okay, well, we know from Newton's second law that the net force can be written another way. Okay, well, let me make this substitution. Okay. Now, I am furthermore going to make the assumption that this acceleration is in the same direction as this displacement. Does it have to be? Absolutely not. There are plenty of physical systems in which the acceleration is not collinear with the displacement. We're going to look at uniform circular motion in a few chapters. That's definitely one of them. The acceleration is actually there orthogonal to the displacement. We'll get there. But if I make this assumption that the acceleration and the displacement are parallel to each other, at the very least anti-parallel, what can I do there? Well, that means that the cosine of the angle between these two vectors is 0 or 180 degrees. By magnitude, then, I'm going to get 1 either way. Of course, I'm going to get a negative sign from 180 degrees. But let's assume for the moment that all I care about is the magnitude. Or let's assume that the acceleration and displacement are in the same direction, along the same line of action. That then will become the magnitude of this vector times the magnitude of that vector times the cosine of the angle between them, which, if I follow those assumptions, turns out to be 1. And I can get rid of the vector nature. I can also bring the mass outside, because we're going to let the mass be constant, of A dr. Right, so just some of what I did. I recognize that the mass is constant, pull it out of the integral. Assume that the acceleration and the displacement are in the same direction. And if that's the case, that allows me to handle the dot product and just get the magnitudes. I've dispensed with the vector nature. This is then easier to integrate. However, there is no explicit relationship between the acceleration and the displacement, so I'm going to have to do a little work. So let me come over here and remind you that A is defined as the time derivative of the velocity. Okay? So I can put that in for A, and maybe I'm a little closer. I'm also going to let dr, which remember is just my placeholder for some spatial differential. Why don't we just introduce an old friend here and call this dx, right? It could be dy, it could be dz. You could do this integral 3 times, 1 for each direction, and sometimes you'll have to do that. But let's just keep it simple and rewrite this as integral from A to B of dv dt dx. So my dr has magically transformed into, my general dr has magically transformed into my specific dx. I'm just looking at just for simplification, looking at one case. All right, so you might look at this and go, okay, you're a little bit closer. You've got, a velocity, and then it's going to involve a position. Well, let me remind you, or maybe for some of you, show you for the first time, how the chain rule for differentiation can help us out here. dv dt is actually equal to the position derivative of the velocity. This is the time derivative. How does v depend upon time? How does v depend upon position is this, times the time derivative of position. And with Leibniz's notation here, it certainly invites us to go, oh, okay, well, I can just cancel that, right? The notation certainly makes it obvious what we're doing. We're not actually canceling a differential. We're applying a chain rule. But it certainly looks like we're canceling, and if that helps us get through it, then I'm okay with that. If you're a mathematician watching this, you can write me angry emails if you want to. I get that we're not actually cross-multiplying here or canceling, but kind of, sort of, right? We're going to get there. We're going to use this notation at least to remind us that dv dt is equal to dv dx times dx dt. Okay, so if this is true, then I can make that substitution here. A to b of dv dx dx dt times dx. All right, so I'm still, my integration variable is still a position, so a to b still works. But I'm going to do a little bit more mathematical chicanery, right? Ooh, sorry, mathematicians. Another chain rule application is going to actually change my integration variable to dv. I'm going to get rid of the dx's, and I'm going to change this to integrating over dv. So, don't need to put that in yet. So let me rewrite this. I get dx dt from here, dv from there. And I've changed integration variables, which means I need to change my limits. I was a position variable from a to b, but now I'm at a velocity variable, which means I need to talk about the velocity that I had when I was at point A and the velocity that I had when I was at point B. So the new limits are related to the old limits because I'm always concerned about these points, but I have changed variables, so I'm going to change limits as well. Okay, all right, well, we're almost done here. dx dt, of course, let me remind you that that is just the definition of velocity. Time derivative of position. I'm going to move this up because I need a little space. And continue here. Okay, so making that substitution, I get that the net work, remember, well, I guess I moved it up too far. The net work, that's what I'm looking for. That's what should be written everywhere here along this column that I'm just a little bit lazy to write. The net work is going to be equal to the integration VA to VB, that is velocity at A, velocity at B, of V dV. And finally, I get something that I pretty much know how to handle. Oh, okay, sorry, back up a step. Sorry, left that out. Okay, I still have an M. Integral of V dV. Well, the integral of V dV is just V squared over 2. Evaluated at the limits. So what I'm going to get is m, and I'm going to write it like this, times 1/2 v squared evaluated VA VB. Now, as I'm looking at it, of course, well, here, let me just go ahead and put this in. What I'm going to get here is 1/2 m VB squared minus VA squared. And if I remember what I'm doing here, I'm moving from point A to point B. In other words, this is my velocity initially, this is my velocity finally. Let me make this specific case from A to B general by recognizing that what I have here is my final velocity squared minus my initial velocity squared. But that, remember, is just equal to delta K. Let me move this whole thing down just a touch. I started off this whole thing by reminding you the change in kinetic energy is written like this: 1/2 m times quantity v final squared minus v initial squared. That's at the point at which I've arrived here. This is delta K. So what does this mean? Well, if I rewrite my left-hand side finally, the net work, and I normally don't, we normally don't write net, we just understand that we mean the net, is equal to, I'll write it like this. It's going to be defined as integral from a to b f dot dr equal to delta k. This little expression here, the outer parts of this triple equation, is what is called the work energy theorem. Remember, and like I said, we normally don't write the network, just like we normally don't write sigma here, although that's what we mean. If I'm looking for the net work done on an object, I can look at the change in kinetic energy. So this flies in the face a little bit of what I said in the last video, that sometimes I need to worry about how the potential energy changes. Hopefully that will get fleshed out as we go on and talk about specific ways that the potential energy can change. But for now, hang on to this. This is a physics law, the work energy theorem. If you do work on an object, that means you're putting in energy, which means that's going to appear as kinetic energy. Spoiler alert, if you go along to advanced courses, you might have other terms here to talk about potential energies. And we're going to actually see that come out in the next section when we talk about the conservation of energy. But for now, just hang on to this. The work energy theorem, you can discover the change in kinetic energy by knowing what the network is. This is also really interesting because now, between the second term and the last term, we have an explicit relationship between forces, displacements, and velocities. Remember, well, at least speeds. There's a speed buried in here. There's a displacement here and a force here. That's what we didn't have with Newton's second law. Newton's second law relates forces and accelerations. If it so happens that my acceleration is constant, I can use kinematics to then relate it to displacements and velocities. But here is the more direct route. Furthermore, the force doesn't have to be constant to relate these things. This works if the force is non-constant. In fact, if the force is constant, you're probably not integrating, you're probably just adding things up. But if the force is non-constant, integration is really your only choice.